Hello. Today I am happy to present to you our paper titled Joint Depth Prediction and Semantic Segmentation with Multi-View SAM. Some recognition scenarios provide access to knowledge about the scene geometry, either through the presence of a depth sensor or known camera poses from calibration. The first example is monocular recognition that assumes knowledge of depths during training but not during inference. Many multitask studies suggest that predicting depths and segmentation simultaneously enhances accuracy of both tasks during inference. These methods, while fast, tend to not be very accurate due to the limited context available in a single image. On the flip side, some recognition methods perform full 3D scene reconstruction and then operate in the 3D space. Although accurate, these methods are slow and require a substantial number of images. This creates a whole spectrum of potential methods operating in the middle ground, for example on just a few 3 to 7 images. That is a common scenario for multi-view stereo methods that perform depth estimation and reconstruction. However, there are not many recognition methods that operate in this space. Our goal is to bridge this gap by introducing a method based on the multi-view stereo paradigm. But before delving into multi-view stereo, let's briefly touch upon the recent transformer-based segmentation models that play a role in our project. Here is the recent Segment Anything model, or SAM. SAM features both a transformer-based encoder and decoder. This model specializes in open set segmentation, generating class-agnostic instance masks that can represent either entire objects or parts of objects. To achieve this, SAM uses a grid of queries to attend over the image features. That way, instance masks are decoded densely across all possible locations in the image. We can leverage the pre-trained SAM encoder to extract rich features for segmentation and replace the open set decoder with a semantic class decoder. The structure of the decoder will undergo modifications, incorporating learned class embeddings instead of positional queries, which we will discuss later in the talk. Each class embedding is decoded into its corresponding class mask. Now, let's delve into multiple view stereo models for depth estimation. Many state-of-the-art models are based on the concept of cost volumes. A cost volume essentially lifts image features into 3 dimensions, estimating correlations between features from multiple views in 3D. In this process, one camera is selected as a target frame, the frame for which we aim to estimate depth. Every pixel of the target frame corresponds to an entire array of points in 3D. This ray represents a set of hypotheses about where the point lands. How do we determine the precise location? Every 3D point along the ray is reprojected into other views, and the correlation-based metric tells us where features agree or disagree. This approach is a well-known classical camera geometry technique that has been incorporated into deep learning frameworks. Cost volumes are known to be unreliable in several scenarios, most notably in textureless regions, where extracting good geometric features is hard. In order to address this issue, our goal is to incorporate the strong segmentation features available in SAM. First, we incorporate these rich semantic features into the construction of the MVS cost volume to get better depth predictions. In turn, we guide the semantic segmentation with the obtained depth maps. Our architecture is conceptually based on MVSNet that constructs differentiable cost volumes. Specifically, features are extracted from several images in parallel with a convolutional image encoder. The features are then lifted into 3D and worked on the reference frame using rays of depth hypothesis corresponding to pixels in the reference view. The cost volume is constructed using correlation of those features, and it is further refined with a 3D convolutional network. The resulting volume encodes probability distribution of the depth values along the ray for each pixel. Final depth predictions are made with soft voting of depth values along the rays. In practice, it's expensive to build cost volumes at high resolution. CAS-MVSNet addresses that, building a cascade of cost volumes, where coarse volume is predicted first as an MVSNet, and finer volumes are constructed sparsely, only using local space around the previous prediction. In parallel, we have the strong semantic features available from the SAM encoder. We propose to combine the two models into a single multitask architecture. We introduce a straightforward feature fusion approach to enhance the geometric features extracted by the MVS encoder with the rich semantic features from SAM. The fusion process includes creating a semantic feature pyramid that aligns with the MVS pyramid and perform point-wise addition. Further, in our experiments, we will show that the fusion method helps addressing several challenging scenarios, particularly textualist regions. In addition to that, the predicted depth serves as a dense prompt for the semantic encoder. The depth features are fused with the image features and subsequently forwarded to the decoder. The only remaining component to examine is the decoder itself. Semantic decoder consists of several building blocks. Lightweight two-way transformer that communicates information between the grid of image tokens and a set of learned tokens is followed by a dynamic mask prediction block. Each of the transformer blocks start with token self-attention, followed by token-to-image cross-attention, a point-wise multi-layer perceptron that updates the tokens, and finally image-to-token cross-attention. This way, the two-way transformer updates both the image features and tokens, creating token-aware image features and image-aware token features. Each token is represented by a single feature vector, while it is tasked with decoding an entire semantic image mask. This information can be encoded into an attention matrix between tokens and image pixels. This operation yields the desired outcome, where each token produces a distribution over the entire image map, which can be transformed into the final segmentation mask. In our decoder, this is preceded with an image embedding upsampling to finer resolution, an additional attention and MLP layer, and the attention matrix is finally constructed through simple matrix multiplication. Moving on to our experiments, shown here are the multi-view depth estimation metrics on the ScanNet dataset, as measured by the absolute and relative depth errors. We start with a version of CAS-MVS-Net that is adapted to the indoor recognition scenario. Our single-task depth estimation model fuses the MVS geometric features with SAM semantic features and does not include the segmentation branch. Finally, the full model jointly predicts depth and semantic segmentation and delivers best results. A valid question to ask is how much 9.0 absolute error is better than 10.0 delivered by CAS-MVS-Net. The quantitative metrics are measured here against noisy ground truth, which creates an unknown lower bound that is greater than 0. In this case, we can benefit from looking at the qualitative results. This figure shows the comparison between the predicted depth maps. It's easy to notice the difference between CAS-MVS-Net and our method, especially on textureless structures like walls. Our method also produces much better edges for structures such as table and chair legs, as well as clutter scenarios. We compare our multitask model to monocular multitask methods for joint depth prediction and semantic segmentation. Here, we only use 3 views, but see a dramatic difference in the depth prediction in the last 3 columns, and a good segmentation improvement as measured by the mean intersection over union in the first column. Finally, even though we operate on RGB images and only reconstruct depth, our method comes close to some state-of-the-art RGBD method for semantic segmentation. And that concludes my talk for today. Thank you for your attention.